Formamidinium lead iodide is a promising material for use in solar cells. It's part of a class of materials called perovskites, whose unique crystal structure gives rise to many desirable properties, including easy fabrication, highly efficient conversion of light energy into electricity, and strong light absorption. Most of the time, anyway. You see, the problem with formamidinium lead iodide is, to put it simply, its color. The perovskite starts out yellow when it's synthesized. That makes it capable of absorbing only a narrow portion of the solar spectrum. Fortunately, the perovskite can also take on a black phase. Getting it there, however, can be a hard process to control. And even though the black phase may be successfully attained for one application, that's not guaranteed to happen for another. It's a problem that's long plagued materials scientists, largely because the perovskite grows much faster than they can track it. Now, using synchrotron-powered diffraction measurements, researchers have watched the process unfold. Their findings not only explain how the pesky yellow phase arises in perovskite films, but they also point to ways of stopping it. Using a specially designed spin coater attached to a synchrotron beamline, the team monitored the chemical species that formed when combining the ingredients for producing films of formamidinium lead iodide. What they discovered was that in films with yellow phases, the perovskite grew as a tangled forest of several competing phases, which were oriented at different angles relative to the underlying surface. To clear this forest and make way for the growth of the black phase alone, the team added another ingredient into the mix, the molecule pentanamidine hydrochloride, or PAD. Fitted with a polar head and hydrophobic tail, PAD could effectively guide the growth of only the black phase of the perovskite. This it achieved by strongly attaching to a specific face of the black phase crystals. In thermodynamics terms, this attachment lowered the surface energy of a specific plane of the black phase beyond that of any other phase, making it the most likely to grow. When packaged into a solar cell device, the all-black phase perovskite outperformed all solar cells in its class, reaching a power conversion efficiency of 25%, among the highest ever reported for formamidinium lead iodide. Larger solar modules were also constructed. The efficiency of these devices is the highest reported for perovskite solar modules, demonstrating the scalability of the new material. The device's potential for future commercialization, however, is still unclear, as their long-term durability remains to be tested. But the findings are promising. Incorporating PAD or similar additives could ensure that researchers consistently get the most out of perovskites and the devices they're a part of.